my background is computer science. So, and especially in France, when we learn computer science, we learn very little, maybe nothing about HCI. So I started doing HCI basically during my PhD thesis. So with all the background that I have in computer science and all the theoretical stuff and so on, it led me to think about the relation between computing and the human and interaction with interactive systems. So first thing that I will talk about is why do we use computer a lot? So the first thing that we use is for very big projects like sending people on the moon. So we could not do this without a computer, obviously. And but at this time we were not thinking about something that is closer to what we could do in everyday life. Now, for decades, we use computers for working. We use them for playing as well. And we also use them for other situations, like when we are running. We think that we are only running, but we are also listening to music. We are tracking all the activities, like the kilometers that you are running, all the physical data and so on. And it's part of the activity now. We can use computers when we are driving a car, like for navigation, for listening music as well. Even when we cook, we can check a recipe, for example. We can use different kind of systems for this. Maybe we want to check how long we have to cook. We have to synchronize stuff. So there are systems for this. We can also use computers when we are playing music, either for a metronome, but it can be the instrument itself that can be a computer. So there are many things that we can do for creative activities. So you know about this, I guess. Also, when we are doing sports, like when we are doing snowboard, and we would like to make a video of our activity, so we can use some sort of computers to make this video. So now we know that we can use computers for a lot of stuff, but what is a computer? So this one is the first computer to ever have an input device. So it was the Whirlwind in MIT in 1965, and it had a teletype writer, which is basically the first keyboard that was ever plugged to a computer to allow somebody to enter data directly during the computation. So it was 1965, and quickly we had some other computers like the Xerox Alto. This one was the first one to have a mouse, for example. And even if this was during the 70s, basically we use the computer still the same way that we use them at this time. A lot of stuff changed, but the overall way we use this kind of computer didn't change that much. But there are some other computers that we use every day, like the one that we have in our pockets. So it can be a smartphone, but it can be a tablet as well. We have this kind of stuff on the wrist, like smartwatches. We have the bigger one as well with the interactive screens. So for the snowboard, we would like to make a video. So we have drones for this. So the drones can follow us and take videos. We have VR as well, so to have immersive environment, and all this stuff are good for some of the activities and not good for the others. And the big idea is how do we match the kind of computer that we use for what kind of activity. And HCI is a lot about these kind of things, because one of the wrong way we do HCI sometimes, and especially when we talk to some companies, is there is a new technology and they absolutely want to do something with this technology, and they focus on the technology itself and not why we are using this particular technology rather than another one. And usually it ends up with a solution that can work to some extent, but when you're thinking about it, the thing is that there are other technologies that work much better for the same activity. Like, I don't know if you saw, for example, the videos for the leap motion, and people were like struggling for 1 minute to click on a button, and they were happy because they could click on a button. When you take your mouse, It's much faster, much more efficient. So this is the vision of most of people in HCI, is that all the computer systems are tools or instruments. It means that these objects are objects that allow us to extend our capabilities. So the vision of Engelbart was usually about a cognitive extension, but it can be also physical extension. The idea is that you, thanks to computers and what I called computers before, which is very large, you can do stuff that you could not do before without these, or that you could not do that efficiently. Like when you're using a hammer, basically you can plant a nail in a wall, something that you could not do with your fingers, for example, because you don't have these capabilities. So the hammer itself doesn't plant the nail. Do you know Gaston Lagaffe? Who knows Gaston Lagaffe? Few people. He's very funny. So he's a specific character. It's the green guy. The guy green. So what he does is always build some weird devices that are more or less useful. And so here I will not translate everything, but basically what he says is that he says to his friend, you know the struggle you have sometimes when you would like to plant a nail to attach something on the wall. And you say, okay, yeah, I know this problem. So I had a solution for this. I made an electric hammer. So you put the electric hammer on the wall, and it plants the nail, okay? Which is fantastic. There is an automatic device that does the problem. What is problematic for you, it does it for you. So it's not just a simple hammer, but it's what we call usually what do we say? A partner, which is you delegate the task to this device, basically, which is an intelligent object, okay? But then his friends say, yeah, but how do you attach this device to the wall? Say, oh, just with 2 nails. So this is stupid, of course, but the idea is that when there is a lot of power in computers, and even recently with all the machine learning stuff, there is the promise that we can do anything that humans can do, but there is the question of why do you ask this device to do it, and can it do it the correct way, and does the struggle of building this stuff worth the benefits that you have when you have it? So this is the question. And still, even a simple hammer can be very powerful. So this one is Mjolnir, the hammer of Thor, and this one is very powerful. You don't just plant nails with this, you can invoke lighting and a lot of stuff. So it's very powerful. So I'll show you now a couple of examples of like digital hammers that I built. So this one, for example, the idea was to revisit the keyboard, because as I showed you before, the keyboard was used in computers in 1965. It was even used in other contexts for a long time before. And the idea was, what can we change in the keyboard? So in this project with colleagues which were in Deutsche Telekom at the time and University of Toronto, we designed a keyboard for which you can raise the keys. So this is the device in action. Oh, I should turn off. I cannot. Sorry. So you can raise the keys basically with this. So what we are interested usually in HCI, we build devices like this, but we are not interested in the device itself, but what you can do with the device and why you are doing this. So what is interesting with this device, for example, is like when you're pressing the control key for invoking a keyboard shortcut, the keys with a keyboard shortcut can raise and you can locate them more easily. Or you can also now access the sides of the keys, so you can push them on the sides. You can also pinch the keys. So if you can access the side of the key, it means that you can map several commands on the same key. And for example, if you want to align you would like to have the align command, you can align left, right, and the center. So you can map all of these on the same key, which is better for remembering the assignment of the keys. And when we did this project, we were thinking, but maybe we can go further, and why we don't move all the devices around, because sometimes we don't use the device, but we manipulate them, but not for interacting with them, but just because they are physical objects that we have on our desk, and sometimes we just want to move them around. So this is an example of what we can do if we have a screen that can move, like we're all doing video conference, or somebody is watching a presentation like this, and we want to show something on the board which is on the side, and maybe you would like to adjust. So there is an interesting question here, is who has the control of the device? Because you could have yourself the control, like I know exactly where I would like to move the screen, but maybe as some cameras exist, they turn automatically to the person who is speaking just by locating the source of noise. But here, if you're doing a gesture, maybe you don't want to turn the camera to yourself, but to what you're showing on the board. And maybe you would like to give the control to the person which is remotely watching what the camera is showing, because this person is the person who knows exactly what he or she wants to see, and maybe is the best to know how to interact. So there is an interesting relationship here about who has the control on the device. There are some other scenarios. We have a lot of scenarios in this paper, like enhanced screening. So like the screen is moving just to give some more immersion when you're watching a movie. Or we can have a people display, which is you extend the area of the screen by when you're moving. It's quite strange. So this question of the degrees of control it's a question that I am thinking about for years, and I will not solve anything for years as well. But it's interesting to think about this, is who has the control and to which extent you have the control, and what do you do, why do you have the control. So there are many things to consider with this. So when I was talking about hammer, there is no one hammer, but there is a lot of different kind of hammers, and each of these hammers are done for something different. Okay, so the function of one is not working for the other ones. So it means that we have a wide diversity of it. And this is what I was talking about with the situation at the beginning, because the device that you would like to use, for example, for listening to music when you're running, is not the same device that you would like to use in a different context, like to send somebody on the moon, even if your iPhone is probably more powerful than all the computers that were used at this time. Anyway. So this is another example of a project which is beyond the desktop interaction, but which is an improvement of an existing technique. So this one here is a ray cursor. It's an interaction technique to select objects in 3D when you're in a virtual reality. So basically, there are two common ways to select objects in virtual reality. The first one is that you grab the objects that you can reach by hand. And if you would like to select something remotely, you have ray casting. So with ray casting, you have a ray, and the first object which intersects the ray is selected. But you cannot select an object which is behind, and the small or very far objects are difficult to select. So the idea here is that we use what is called the bubble cursor that was defined for 2D interaction. We extended it to 3D interaction. Basically, we select the target which is the closest to the cursor, which means that we need a cursor on the ray. So we added this cursor, and we can control the cursor with a touchpad that you have on the Vive controller. So this is how you interact with it. And then we have some semi-automatic modes in which when the ray intersects an object, the cursor moves automatically to this. So it means that you can still take the control of the cursor if you would like to adjust, but we take the advantage that you can select and switch between different targets quite fast. So this is interesting. Now we can do something even more interesting, like instead of just modifying an existing technique, we can change full paradigm. So one of the paradigm that I was interested was direct manipulation. So does everybody know what is direct manipulation here? Yes, no, I will remind a couple of the basics of direct manipulation. Basically, direct manipulation is what made the success of a graphical interface over the command line, which is all the objects of interest must be visible. You must have a continuous feedback of your actions. You must have the result of your action must be visible, and so on. So you have many properties that ensures that when you're doing something, you know what's going on, and you know what you can predict what will be the result of your actions, and so on. The good example usually people give is when you're doing a drag and drop with a file, for example. When you grab the file, you have a shadow of the file that you're moving around, so that you know that you grabbed an object and you have it in hand, and you know you can see the place that you will drop the object if you release the button. So you have visual feedback that gives you an idea of what's going on with what you're doing, basically, which is very good for interaction. The thing is that direct manipulation, at least how it was defined in the 80s, it relies on visual feedback, and there are some properties that are very closely related to the properties of vision. And so we wanted to do the same, but with haptic feedback, specifically with vibration feedback. So the idea is, how do we reproduce all these properties? So I made a wristband. So this wristband, the idea is to make a one-dimensional circular display, okay? And to give you a sense of what's going on, I do a visual animation. So imagine that this is 1D one dimension space around your wrist, so you can circle it if you wish. The first thing you need is a cursor. So it means that you must have a cursor that you can move around in this space, okay? And you need to be able to locate the object of interest, like the object that you would like to point and to select and to manipulate. So with this, imagine that you have this cursor, and then when you move them around, if you're on a target, the cursor changes in some way, or at least gives you a feedback which is different from the feedback it gives you when you're not on your object. So this is the basics that we need to provide direct manipulation with a haptic display. So this is the device. So the device, basically, this handles all the vibrations, and this is a kind of touchpad, and with this touchpad we can manipulate the cursor. So basically you have input and you have output. And for representing the cursor, we use a specific tactile illusion, which is the phantom vibrations. So we have 4 vibrators all around the wrist, and we manipulate the amplitude of the vibration between 2 actuators. And by doing so, we can feel like we have a virtual vibration at any point around the wrist. Okay, so the amplitude will be coded with the color. So you can see that you can feel this point, but this is the amplitude of each actuators. So with this, we can feel vibration anywhere. And if we control the position of this with the touchpad, like with simple flicks in one or the other direction, you can move this cursor and you feel like you're controlling this cursor. Okay? And then to encode if you're on a target or not on a target, we just use different frequencies of the signal. So frequencies which are so different that you can feel clearly the difference between you're on a target and you're not. And when you do this, basically you have almost all the properties of direct manipulation. The one that you don't have is you cannot see all the targets at the same time. You don't have an overview. And this is something that is very complicated to reproduce with tactile feedback, but The thing is that since it's a one-dimensional screen, basically, and that you can move it around, it means that you cannot avoid a target. If you can explore the whole space, and you know that if there was a target, you cannot miss it. So basically, there is a discoverability that compensates the way that you cannot see all the targets at the same time. So basically, it extends in some way this property of direct manipulation in different contexts. And then you can do interesting stuff like unlocking your phone. So imagine that this is the space, and then so you feel each time that you're crossing a number, and with proprioception you know which is the number that you would like to select, and then you select your code and you unlock your phone. So I was talking about hammers, and there are a lot of different hammers, but you know what we say, if you only have a hammer, everything looks like a nail. So maybe we want to do something which is not a hammer. So we have a lot of different objects which are very useful, which are not hammers, but which are equivalently powerful. I can show you some examples. So I will not go into details in this one, because you can talk to Alf about this, which is the FlexStylus project, which is started with Nick, who was a master student here a couple of years ago. We published a paper about this. So basically, it's a stylus that you can bend, and this gives additional degrees of freedom, and we can do wonderful stuff with this. And Alf will have an experiment to run soon, so he will search for participants. So if you will try and know about this, just ask him. There is another one, which is this one is an interesting project. It's with tactile interaction. And the question was, how could we use the information if we could know which finger is touching the surface? Basically, what could we do differently if we can know if it's this finger or this finger which is touching your tablet, your phone, your tabletop, or whatever. So we did a lot of stuff with in all these contexts. So in this video we have an example with the tabletop, with the phone, and with the tablet. So for example, this is a way to select commands. So we'll see more in detail later. But the idea is that we can do the equivalent of keyboard shortcuts, but with a tabletop. This is the idea. So the first one is with the smartphone. So the obvious stuff is that with one finger you can do the lowercase, and another one we can do the uppercase. You can also select commands like copy, paste, and cut. So with the finger of the the left hand, you can open the menu, and with the right hand, with this menu, you can select the command which was in this menu. So this is the idea. With the tablet, we can have, for example, an application for editing a PDF. So with one finger, you can scroll the document. With the other finger, you can highlight in the document. So you can also invoke a menu. And with this menu, you see that you have 4 items that you can keep with the other hand. And these 4 items are basically the items that you have on the 4 fingers on the other hand. And you can customize all the properties of, for example, the brush that you are using for interacting with it. You can still select commands like undo or redo. And with 2 fingers, you can also zoom the document. So this is an interface for customizing everything. You can also add comments. You can select text. And the tabletop application, so this is an example of like graphic drawing. So here, the idea is that the left hand is somehow what we use as the control, the shift keys, and so on. So it's a combination of modifiers So with all your 5 fingers, there are 31 combinations that we can perform, which means that we have 31 palettes of commands that we can map to the 5 fingers on the other hand. So it means that we have just an enormous space of commands that we can map to just fingers. And here you can see as well, again, that we are not just interested in the technology itself. Like for tracking the fingers, what we used is it's a device, what is the name? The GameTrack device. So this device was used for golf simulation. And basically it's, you have a string, and the string is mounted on a kind of joystick. So you have the 2 angles of the joystick and the length of the string. And with this you have a 3D position, which is very stable and precise. And we have 10 of these devices attached on the top. And with this we have the 3D position of all the fingers, and then we just have to match these with the 2D positions on the surface. And basically with this we just prototype how we can use this information if we could have it. And then of course this is not the technology that you will have someday if this kind of property is implemented in a device. But you can prototype this very easily with this. So in this other project, the idea was to revisit the dashboard that you have in a car. And so it was a project with industrials as well. The idea is that they would like to do new dashboards, but they want to remove the physical buttons. I'm sad about this because I like physical buttons, because physical buttons are very useful because you have haptic feedback. You know when you're pressing them, you know when it's working, when it's not working. But they don't like it because it's complicated to manufacture. You can have dust in between, it can break, and if you would like to change the interface, you cannot because the position of the button is fixed and you cannot change it like with a simple update. So they would like to do like buttons on touch screens, but still have the haptic feedback. So this project was about doing haptic feedback and sensor as well that you can just insert in a mold when you're molding the dashboard. So basically we had a company which does plastic objects like for dashboards or for whatever. And the idea was how can we add some sensors inside this. So one of the partners, CEA in France, they have a big facility for printing electronics, sensors and actuators. So basically the blue stuff is it's a piezo ink. So these are vibrotactile actuators which are printed. All the traces are in a silver ink, so it's conductive, and it's printed on something flexible. Sorry for the noise. So the idea is that you have to clamp this, because if you don't clamp it, the vibration dissipates and you cannot feel it in the finger. So there is a lot of question about this. Some people in the project did simulations on how it should vibrate. It means that what thickness you need for the actuator, what are the size you need and everything. But at the end, they don't know exactly how people use it. So this is what we were doing in this project, is how do we use it? How do we prototype this kind of device and so on? So here, yeah, we have the sensor, we have the actuator. This is all the driving electronics. And so we did this kind of buttons. And the idea is how do we reproduce the sensation of pressing a button when you can only do a vibration, and it was, in this case, very light vibration actually. So this is, I don't know if somebody know about Pure Data here. People from audio research use a lot this kind of stuff. It's a visual programming environment, and the idea is that you have data flow and so on. And so this is very convenient for manipulating like sine signals. So since it's a vibration stuff, you could play music with this as well, because it's just a different frequency. So we did buttons like this. So we had a demo at Twist in which we explain a little how we did the buttons, and we currently have a submission to explain it further, like the slider and everything. And there is a plan to do a touchpad. The project ended before the touchpad was implemented. And this is a project that I'm starting right now, that I already had an intern working on this. It's completely different from what we saw before. There is no new device or whatever, but it started with a personal project, because I do genealogic research about my ancestors, and they come from a lot of places, like in Poland, in Italy, in Germany, in France, everywhere. And in all these places, even some of them were in the US at some point. And when you're collecting all these documents where you're searching for information about your ancestors, the problem is that they are in other languages, they are not well written, it's very difficult to read them. But as a HCI researcher, I was like, but a lot of people could read this, so why couldn't I make a kind of tool that helps me to read it, or to progress in this kind of skill to read it? And there are obviously a lot of people who are working on automatic methods for this, but we'll see that it's complicated for them. So, for example, these are information about my great-grandfather. And if you look at this, so he came from Poland. And on my grandfather's birth record, the city of birth of my great-grandfather was written like this. This is a census, it was different here, and another census, it was different here. Because these people did not know how to write, so they spell it with an accent, and it was difficult for the others. So even if you have something automatic, the automatic algorithm has to know that even if it's not written the same, this means the same word. So this is something that we can do as humans, because we are very flexible, but that can be very difficult for a computer, for example. And the same for another one. And I had a lot of struggle to locate this city actually. So, for example, this one is the birth record of my great-grandfather. So you can see that it's written in Russian, because Poland was partly Russian at this time. And this is not so difficult for somebody Russian, even if some letters changed, but still it's complicated for me. Which is interesting is that fortunately they wrote in Polish the name of the father, of the mother, and so on. So there are some clues like this that we can use. But this is like very difficult. So this is a project in France that exists for transcribing documents with automatic methods, like with machine learning stuff. But as you can see, the writing is very, very regular. And there is no overlap. There is a big gap between the lines and so on, which means that this situation is very easy, actually. And even with this, the results are not so good. Why? Because these are machine learning approach, which means that you need a large database of examples to give to this algorithm so that it can give you a result. But when you're doing research, like you got only one document, you don't have this database, which means that what can you do if you don't have all the knowledge that the algorithm requires to do the job? And in any case, if you would like to build this database, you have to do it by hand, because, well, the automatic method needs the data that you're building. So at some point, you need to do it by hand anyway. So the question is, why don't we do something which is a tool that helps you to do it manually, and then that can leverage information that you can get from automatic methods? So these are examples of something which is much more complex to even for an algorithm. So this is in German, I think, and some of them are in Latin, but this one is German, yeah. And sometimes just very complicated, because at the time it was like priests, they didn't care about this, and they just wanted to finish this as soon as possible, so it was quite complicated. So let's take this example of my great-grandfather. So this is in Russian, complicated to read, but we can do some stuff. Like for example, we can raise the contrast, so it's a little easier to read. At least this one was well scanned, because sometimes you don't have the same background in all the pieces, so it's more complicated. So this one is okay. What you would like to do is to separate the lines so that you can clearly see which part of which is from which line. But this is complicated because, for example, here you don't know exactly which pixel is from which line, and sometimes it can be from both. So maybe we can do something that can separate them manually, automatically. It's very difficult. There is research about just separating identifying lines in documents. And this is something that I prototype with GIMP, for example. I was like, what if I had a tool with this tool I could select a word, because I know where are the pixels which I'm interested in, but at the same time I use simple algorithms to separate the background from the foreground. And if I had this, for example, so this is my name in Russian. Okay, imagine that in a lot of documents I know this name even if I don't speak Russian, I don't read Russian, but now my brain is used to this and I can recognize this quite easily. I have a neural network somewhere, thankfully, that works, thankfully, and I can recognize this when I'm seeing it in a document. So I can select it in a lot of places and I can build a kind of database of a lot of ways to write my name. So for example, in Russian, in Latin letters, this is in Russian but with like pretty letters or printed letters and so on. So I can make a database with this. And now there is something much easier to do for algorithms, is to say, okay, I have this word, can you search in all these documents where you see an occurrence of this? And this is much easier for an algorithm. Okay. Now some other stuff that we can do. Of course, we can go to the letter level. And so here I selected a lot of words, and when it was the same word, I used the same color. So sorry for color blind people, but basically here the idea is that this is the date. Here, this is the name of the father. This is, we can see it here all the time. This is the name of the city. Here is the name of the mother, name of the child, and so on. There are several names. And there is something that I noticed. For example, here, yeah, I saw this. I have no idea what it means, but I saw this, and it was all the time after a name, something, a place, something, and this. And in fact, I realized that this means years old, which means that the number here, the word here means the age. So we have the name. This happens to be the job, occupation, the place where they live, age, and the stuff that says this before was age. So you see that even if I don't speak Russian, if I cannot read Russian, I can recognize quite easily the structure of the document and find the information that I'm looking for. So which means that I don't need to have something that translates everything and recognize all the words and so on. And here, since I say that I know that this is a job, I can select this word and say to the computer, can you search this among all the words that are labeled as a job? And it reduces all the possibilities, and it's much easier for it to find the good solution. And there are a lot of words like this. For example, the months. When you have a date, you know that this is a date, so you know that one of these words is somewhere here. So you reduce all the possibilities. These are all the numbers. If you have an age, for example, the age of the father is between 18 and 45, let's say. So it's quite easily, because it's in the 10s, in the 20s, 30s, eventually on the 40s. But you can find it easily. And with practice, then you're trained and you can read it by yourself. And this is what is interesting. So I translated a lot of stuff. So this is the tool that this intern did. So it was just the selection tool, but it works quite well. So basically this is a brush, and there are 4 parameters: the XY position, the size of the brush, and a threshold. So here you have the histogram of the pixel in the area, and the red one is the threshold. And by just adjusting this, we can see with direct manipulation which pixel I'm going to select, and it's very easy to select words like this. The good thing is that, well, the problem is that we need 4 parameters. The good thing is that we have flex stylus. So, and now we can do a lot of other operations with selection, like we can do Boolean operations, because here we selected and we don't want this part, so we can remove it with lasso selection, for example. So how many stuff we can do. This one was another ambitious stuff that we were thinking about, like when you select something, then you can show the stroke that you use, and maybe you can change the parameters at each point of the stroke, like to, for example, change the threshold at some point, because at some parts the contrast is not the same, and so on. So we have a lot of computers that can be useful in a lot of cases for a lot of stuff and so on. But the thing is that with all this computation progress, we are thinking about why do we still have to do something? You know, like people think that computers will do everything, and what remains for user? This is an answer, for example. The idea is that there are still tasks that we would like to perform by ourselves, like all the creative stuff. Like, there is a philosophical question behind this: is that is art still interesting if it's not done by humans, for example? This is a question, because why do you like art? Is it the object itself, or is it the performance that led to this object? So maybe, and it's also enjoyable to perform by yourself as well. So when you're painting, but when you're playing music, sometimes you're just happy because you're playing this music, not because you like to hear it. So you still want to do some activities. You still have desires, and you want to learn some stuff. Like, for example, in the case of these documents, I still want to be able to translate them by myself, to be able to read them by myself. The idea of the tool is that I can use it to do the job, but as well for learning how to do the job by myself, so that when I have a document, I can read it, because I know that some people can read it like without any tool, so maybe I can do it as well. So why not? But we have computers, and the question is, what is the difference between a computer and humans? And what can computers do, and what can humans do, and which part of the task that we let to the user, which part we let for the computers. And if we would like to solve this kind of question, we have to know the limits of what computers can do and what humans can do. So, and the tiny part of what computers can do is algorithms. Algorithms can do a lot of stuff, and we well know what algorithms can do because we have complexity and calculability, and these are two fields of computer science that studies what an algorithm can do and at which efficiency it can do this. But this is something which is very difficult to do for humans, because this works for algorithm because it's a rational. They are rational. It means that they are built the way that we want them to be, and they do what we want them to do. But humans are not the same. If you look at, so this is the serial action from Don Norman. You probably know this. Basically, when you would like to do something, you have a goal, and you have to specify intention, actions, and you have to perform these actions, and you act on the world with this. And in exchange, the world changes, and you perceive these changes in the world, you interpret them, you evaluate them with respect to your objective, and then you understood what you do, or what are the repercussion of what you did on the world, and so on. So this is how we interact with the world, and in particular the interactive systems. The idea is that Computers can work the same way. Basically, there is a world and they have sensors. The sensors get information. So they are transformed into input events, input phrases, and then the application receives all this stuff and they do something. And this something produces an output. So for this, they encode parts of these data that they have internally, and these are transformed into commands to devices, and these devices produce an effect on the world. And basically the idea is that it's almost the same way of working, and probably because we know that we are working this way, and so we design all the devices the way that we know it works for us as well. And the idea is that we interact with a lot of stuff in the world, including some devices, and the devices as well. So it means that the devices are not just Turing machines that are working with a known input, but it's a machine that processes an infinite stream of inputs that come from a lot of different places. And this is what happens when we are interacting basically with device, which is we have our sensoromotor loop, which is our understanding of the usage of this device is a loop between our action and perception of the results of these actions. And the system has an execution loop with input and output, which is exactly the same, and the things that we connect them together. And then there are many questions that we can think about. I will not go into details. I will finish with this. But the idea is who has the initiative in this? So if the user has the initiative, this is the hammer, what I was talking about before, which means that you're choosing exactly what happens. And there is also the partner model, which is the system is doing the things for you. And sometimes you can change the behavior, you can observe, you can say, okay, this is not exactly what I want, but basically the machine does the job. And you have this vision, which is mediation, in which there are several users, and the system is just a way to connect the people together to do the action, but just between them. So this is a big question that we have about computing system is why do we use them, and what should be led for the user, and what we would like the computers to do, basically. So there is a lot of stuff to think about this, and it's not only about computer science, not only about design and so on, it's also philosophy, it's about people in computing and so on. So there is a lot of discussion with a lot of people for this. So I finished. Thank you very much.
Any questions?
The first one is the most difficult one.
I'm really curious about these printed sensors you were talking about.
Yeah.
Like you said, you teamed up with a company for that? So is there any part that you guys have to build? Or
So these are built by CEA. So CEA is like a big research institute in France. There are several facilities, and the people who are doing this, they have a very big facility for printed electronics and stuff like that. They can print LEDs, for example. They can print a lot of stuff. And so this is very precise, so it means that they need a clean white room for printing this. So this is not something that you can do in your lab, unfortunately. Maybe someday. Some people do, because it's screen printing, so basically you have like a stencil, and the only thing is that the thickness of these actuators is like 4 microns or something like this. So this is why you cannot just do it by yourself. But maybe someday it will be more accessible. We wish.
And when you had the one that changed from like vibration to sound, was there anything that you did? Like,
we just plugged it to the audio output of the computer. Okay. Yeah, because basically what it does is that it vibrates. You know, piezoelectric materials. The thing is that they are reversible. It means that if you give them voltage, they change their shape, and if you change their shape, they produce voltage. So we use it in the other direction, like in lighteners or lighters. Yeah, in lighters, when you click on this, it produces a little electricity, and this can light your lighter. but we use it usually in the other direction, like this, where you give it voltage and you change its shape, and by doing this you can vibrate it. So the only difference between sound and haptic is just the frequency, which is not the same. Yeah.
For the text selection project,
Yeah.
as OCR, you try to figure out letter by letter for each words and compare all of them with your database.
So for now, I don't have database. For example, the only part that was done was just this selection tool, and the rest is a project build. So I'm searching for fundings for this, so for students, for everything basically. So, but the problem I see with the letter level is that sometimes you don't know what stroke is which letter and so on. It's very difficult to separate the letters in some words, especially in some writings. Like if you look at the German writing, like before the 20th century, a lot of letters were very similar. So it's very difficult to separate them. This is why you don't even know how people could read it, but yeah.
Maybe it's easier to separate the words, not the letters.
Yep.
Just, make some mathematical algorithm that you can, after that, manually adjust, like it's made some errors.
Yeah. This is a question which is quite complicated, especially is what do you want to do automatically? Because sometimes if you were not involved in some part of the process, there is a part of the knowledge that you don't have, that can be missing when you would like to do the next job. So this is a big question too, and we are not there already. Yeah.
A remote attendee from Ontario Tech was asking about the tablet interaction example with the individual finger tracking and actions.
Yeah.
Was there any evaluation performed to see how long it would take for a user to get proficient with it?
Not an evaluation about this. In fact, there was one of the big questions about this was the discoverability. It was discoverability, the ability to memorize all these commands, but because it's good to have a wide design space, but then how would you remember where is where? So we didn't measure something about this, but what we argue is the ability to explore all of them, which is when you're selecting the commands with the left hand, basically you perform a chord with your fingers, and when you perform this chord, you have a feed-forward information about the available commands. So by just moving your fingers, you can explore quite quickly the commands. And the idea is that in this kind of software also, you always use the same commands. So at some point you're used to it because you just regularly use always the same commands. This is something interesting actually, because once I was talking with people from Autodesk, and so they do very complex software like Maya and so on. They have thousands of commands, and they have interesting data about how people use the commands, and they have ways to visualize the profiles of users. Like they have a kind of chromosome, and each line is a command. And the color means the frequency they use this command, and by this they don't identify exactly which command people use, but they can see the patterns, and sometimes they can recognize patterns from users to the other ones. So they see that these users use roughly the same commands because their chromosomes look the same, and they also use this information, like if you're using a lot of commands that another user is using as well, they suggest, oh, maybe you can use also this one that you're not using, but this user use it a lot, or this user or this group of users. So they can suggest commands like this. So we don't go that far in this project, obviously. Yeah.
About the finger tracking in the tablet.
Yeah.
So you can design it for whatever task that you want. It should be pre-designed, or for example 3D modeler can use it as they want, or the people who want to do selection can use it as they want, or it should be pre-designed everything.
So the thing is that in this project, the idea was to explore the design space. So we provide a framework, or this is how you can interact with this device which have this capability. But then the actual mapping, the actual application, we just provide some samples to see this is how you could use it if you have this kind of application. But then the designer should define his own way to map the commands and so on. So we didn't search for an optimal mapping of commands and so on. This is not the point here. The point here is just to see that you have these capabilities, and here is how you can map them in the general way, but then the particular implementation is something that should go more in detail for those who are interested in this.
Any other questions?
Okay, well, thank you again.
Thank you.